Hey everyone, and welcome back to my series on logic and set theory. So, uh, last time we ended with finishing up a syntactic understanding of propositional logic, and finally we are prepared now to move into the thing that we're actually interested in, which is the semantics of propositional logic. And in fact, let's instead say what we're actually doing, which is we're finally building the models for propositional logic. Okay, so before we get into the definition of what a model what a model in propositional logic looks like, let's remember what we wish, right? What we want. So basically, what we want is that models are possible worlds. And that's a I've explained this. I explained this deeply in the first video, so refer back to that if you forget exactly what intuition I'm referring to by saying models are possible worlds. But let's try to understand what a possible world looks like in propositional logic. So remember, syntactically in propositional logic, I'll have like my set of sentence symbols, maybe P and Q. I like using them; they're easy, right? Um, and so we might have sentences. So, for instance, there's sentences like this one, not P or P. And of course, this sentence is always true, regardless of the value of P, right? It doesn't matter if P is actually true or false. This sentence will be true. And then there's other sentences, like the sentence P implies Q, which could be true or it could be false. Of course, again, depending on the values of P and Q, right? So, of course, if P is, for instance, false and Q, sorry, I have this backwards. If P is true and Q is false, then this whole thing happens to be false. But, if P is true and Q is true, then it would be true. So, I can write down a sentence like P implies Q, and that's a sentence that, in some possible worlds is true, and some possible worlds is false. So, what you may be observing is that for propositional logic, what a possible world is actually just which of our sentence variables, which of our sentence symbols are true, and which of them are false. So, with that in mind, let's begin a rigorous definition of a model. So, a model, and let me use a different color here. So, a model A for sentence symbols S simply is a subset S. So a model for a set of sentence symbols is actually just a subset of sentence symbols. And what we'll mean is that, and now this is, I'm going to make this clear, that intuitively, right? This is not part of the actual definition, right? But this is intuitively what we hope is that P is in A means P is true, and P not in A means that P is false, right? So basically, I just what a model is for propositional logic is basically just I'll tell you which variables are true. here's the variables that are true. These are the ones that are true, and the ones that aren't here are the ones that are false. So that actually, this is really simple. This is really simple because propositional logic is so simple, right? Propositional logic only consists of propositional variables that are either true or false. So of course a model of propositional logic is only going to be, just telling me which propositions happen to be true, right? And so you can think of this as sort of a higher level look at first order logic. Eventually we'll get to predicate logic or first order logic, and that's the one that's interesting. And that's the one where we'll eventually introduce the symbols, the for all and there exist symbols. And these are the symbols that are actually truly foundational to developing mathematics. But really, we'll use, and we'll write sentences down. Eventually we'll reach the point where we can write sentences like x equals 0. But this sentence itself, or rather, we'll be able to build a syntax that writes sentences like this, but this is just a sentence, and everything we'll say about propositional logic will still apply if you zoom out and forget about what your sentences look like and only consider the sentences themselves, right? So basically, at the high level, a model is telling us which sentences are true and which sentences are false. When we zoom in further and we say, no, you have to tell me more than which sentences are true and which sentences are false, or rather what I'm saying is when you zoom in more, we're going to make the models do more. We're going to make the models not only tell us which sentences are true, but they're going to have to exhibit an object in which those sentences are true. And that will be what's actually interesting to study. But for now, the object in which the sentences are true is just which sentences are true, because, of course, we're only working with sentences yet. Okay, so I think I rambled a lot, but I think this is a really good thing to get fully clear on, is why such a simple definition for a model suffices for propositional logic. And you'll see when we start defining these for predicate logic, these models are going to be far more interesting and far more complicated, but it's helpful to begin with something simple first. Okay. So now we know what a model is, but the whole point of a model is, the model is a possible world. So what use is a model if we can't tell when a sentence is true in a model? So what I want to answer this. So truth in a model. So let's try to understand what it means for a sentence. And right, of course, we already know which sentence symbols are true, but a sentence may be, like we said last time, conjunctions or negations of sentence symbols. So let's try to understand what it means for a sentence to be true in a model. Okay. So let's begin the definition, and it'll go as follows. So for a sentence phi, and I always like using a different color for the variables so it's more clear. For a sentence phi, we say for a sentence phi and a model A, and models are basically just sets, so I'll be using capital Latin characters as is typical for sets, right? For a sentence phi and a model A, we say, or maybe I'll do this on the next slide. So we'll define A, and I'm going to read this. The way you ought to read this is phi. A, you could read this as A is a model of phi, or phi is modeled by A. I think it's hard, but we'll what this will be read as to us formally is that A. This is the same thing as saying A is a model of phi. I'll probably in shorthand be saying A models phi, because that's, much simpler. And that's what I don't know how formal that sort of speech is, but we're defining this, and this is basically, this is a relation, right? You've seen relations before, like stuff like, obviously stuff like less than or equals. This is a relation, and it relates a model A and a sentence phi. And what this means is, equivalently, this is also saying phi is true in A, okay? So that's what this says, right? The A double turnstile phi is saying that phi is true in the model A. In the possible world that A represents, phi is true. So now that I've introduced the notation, let's define it. And this definition will be very familiar. So define A models phi as follows. And you will notice some similarities. So if phi is actually a sentence symbol, then A models phi, or why don't I say, actually, if A is equal, or phi is equal to a sentence symbol P, P is a sentence symbol, then A models phi if and only if P is in the model, right? So this is what we would expect, right? Is, like I said, the models, so like I said, the models are the collection of all sentence symbols that are true. So of course, A models P, a sentence symbol P, A models P if and only if P is in the model, right? It makes sense that this is the definition we would want. And now, point 2 and point 3 ought to seem very familiar from last video. So if phi is not psi, or I won't write it, but if phi is not psi for a sentence, or maybe I will, for a sentence psi, then I want to use a more poppy color, A models phi if and only if A does not model psi. And then finally, I'm actually going to scroll down so I don't have to erase this all. And then finally, point 3, if phi is, and right, guess what this means. If phi is psi and pi, then guess what we'll say? A models phi if and only if A models psi and A models pi. Okay, so let's break this down, and let me see if I can get this all on one screen. Looks like I can. Okay, so let's break this down. Again, we're using a recursive definition, and again, we're using a recursive definition on the length of a formula, right? So this is a pattern that we're going to see over and over again, that this is how we the whole point is we built sentences from smaller sentences syntactically, so semantics are defined almost the same as syntactics, right? And that's good, because we're going to try to build, the next goal that we're going to have is building a relation between semantics and syntactics, right? So importantly, this definition looks like it looks like I did nothing. It looks like I did exactly the same thing. But what I now introduced, right? Remember before, I was just telling you what sentences are. Now I'm abusing the syntactic understanding, right? These are syntactic ideas about sentences, that sentences are always either sentence symbols or negations of other sentences or conjunctions of other sentences. And I'm abusing those syntactic definitions to bridge into actual semantic understandings of whether or not the sentences are true or false. So this is where we have defined that this guy is negation and this guy is conjunction, right? Okay. So hopefully this makes a lot of sense. And the idea is it's what we want. It's the hope is that, you know, we've built exactly what we want. That this is a, you know, that you know, A is modeling phi if intuitively phi ought to be true given that everything in the model A is true. That's what we've built. And I think it's really clear. Like, this should be, it may not be clear yet how to prove this. That, you know, what I said, right? That, you know, A models phi when we expect A to model phi, right? That, you know, A models phi if and only if, or let me say this again. So A models phi if and only if phi is true when everything in A is true, right? That's like kind of the aim. And it's not yet clear how to prove this, but it should be intuitively clear that this is true, because I've defined points 2 and 3 to align with our intuitive understanding of what not is and what and is. Okay, so that's the first step of model theory. Let's move forward from this. And let's move forward from this definition of A modeling phi. And we'll define a handful of other things. Or in fact, we'll define one more important thing, which is a notation that, here comes another definition. So we will say that, and this is what we're going to say, nothing, just a turnstile phi if for every model A models phi. And we will read this as equivalently phi is valid. That's the word we're going to use for this. So that's the definition. Let's unpack it now. The idea is phi is something that's true in every model A. So regardless of my choice of model, every possible model models phi. And if that's so, we will call phi valid. So before I move forward from this, take a moment. Try to write down, right? Phi is a sentence. Try to write down an example of a sentence that's valid. Okay, so hopefully you thought about that. A sentence. Here's a very simple example of a valid sentence. This sentence is valid, right? It's an example I gave earlier. Not P or P. That's a valid sentence. So valid sentences are sentences that are, you know, and innately what it works out to be is that sentences are valid when they're true regardless of the assignments of the variables, right? So no matter if P is true or false, phi is true. So, okay, so this is, it seems like I'm not actually doing anything differently. It seems like I'm not doing anything differently yet from what you have done. Right? When you've thought through logic, you've built you've basically built tautologies and truth tables, right? That's what you've done before. You've basically said, you know, a sentence is a tautology if every assignment, and actually the next thing I'm going to do in the next video, we're at 19 minutes, so I'm going to stop here, but the thing I'm going to do in the next video is define the more familiar notion of tautologies and truth tables and stuff like that. But the one distinction is that what we have done is we've constructed an object that sort of represents the world we live in, right? So this is very similar to the idea of, a sentence is true, or, it's true no matter what, or it's true based on if, P is true, or it's true if P is false, right? We've built that up, but we've built that up in a particular way using these physical objects models, right? We have an actual set that represents that, and that was the goal of this. So I think I'm going to stop it here because we're at 20. That is, what a model is in propositional logic. And our goal for next time will be to build up this much more syntactic notion of what it means for something to be true, and show that our semantic notion of building up models aligns nicely with the mechanical calculation of truth tables, and that what we did, yes, is what, or that that we've built models in a way where things are true, or that when a model says something is true, it agrees with the truth table, right? That's what we want to show next time. So anyway, thank you for watching, and I will see you guys around.